This is track 14, workshop 4. So if you want to know about design and testing of dielectric barrier discharge torches for wound healing and sterilization, this is the right place. My name is Carol Carey, and I'm also an alumnus of JHU at the Whiting School of Engineering. And I'm here, it's my pleasure to present today's distinguished student researcher. She's a senior in high school. Her name
Recording in progress.
Her name is Krishnaveni Parvataneni. Did I say it right? So, and she's from Basis Independent, Silicon Valley, USA. It's all yours.
Hi everyone, my name is Krishnaveni and I'm a high school student at Basis Independent, Silicon Valley. Today I'm going to talk to you guys about some research I've been doing for the last 2.5 years at San Jose State University and Intel Science Research Institute, and the topic of that is designing and testing dielectric barrier discharge plasma torches for wound healing and sterilization. So a bit about what I'm going to talk about today. I'm going to give you guys a brief introduction to what exactly plasma is, then a demonstration of a dielectric barrier discharge, and then I'm going to talk a bit about the applications of DVD plasma in the medical field, along with traditional, the design of a traditional DVD torch and the limitations of that design. And then I'm going to go into new types of plasma torches that we've designed at our lab, including the multi-electrode plasma torch, the plasma sheet generator, and the multi-facet plasma torch. And then I'm going to talk about plasma torch characterization, including spectroscopy analysis, which is used to analyze the various temperatures of the plasma jet, and the protocol for bacterial growth that was also used in testing our plasma torches. So in this excerpt from a paper, or a chapter of a book written by Wiseman, it says this chapter contains a short discussion of some fundamental plasma phenomena to introduce key plasma properties like quasi-neutrality, shielding, particle transport processes, and sheath formation. In section 3, we will describe the simplest plasma models, collective phenomena, drifts, deduced from single particle trajectories, and fundamentals of plasma fluid dynamics. The last section discusses wave phenomena and homogeneous, unbounded cold plasma. So basically what this means is that when we learn about plasma in physics classes, or in any science class in school, we learn about it this way. We first learn that a solid is basically a bunch of molecules fixed in a lattice. And then when you warm that up a bit, you have a liquid, which is molecules that are free to move, but they move a bit slowly. Then when you warm that up even more, you get a gas, which is the molecules are free to move, and there's a large space between the molecules that can move even faster. And then when you get to plasma in science classes, you learn that it's ionized gas, or gas with the ions and electrons free to move independently of each other, and that's like the hottest state of matter. But there's really more to it than that. Plasma is ionized gas that meets a few more conditions, including the plasma approximation condition, the bulk interactions condition, and the collisionlessness condition, all of which I'll talk about in coming slides. So before I go to each of the 3 conditions on plasma, I'm going to talk about some definitions. So imagine you have a probe and you're putting it in, you're putting it in plasma with a bunch of electrons. So 3 things you'll need to know are the Debye length, the Debye sphere, and the Debye sheath. So the Debye length is basically the radius of this Debye sphere. So let's start with the Debye sphere. The Debye sphere is the radius of is the sphere itself that that forms with charged particles around the probe that you're putting in. And this sphere, anything outside the sphere, is said to not have attractive or repulsive forces with the probe, whereas anything inside the sphere has attractive or repulsive forces. The Debye length would be the radius of the said Debye sphere. So over here we have a Debye sphere. This would be the Debye length. And then a Debye sheath is very similar, but if your probe was a rectangular plasma sheet, then you would get the Debye sheath on both sides of the plasma sheet. Okay. So to the first condition, that's called the plasma approximation condition. And in this condition, there's something called the plasma parameter, which basically represents the number of charged particles within the Debye sphere. So basically every charged particles in the sphere given over there. And that plasma parameter has to be sufficiently high as to shield the electrostatic influence of the particles around the sphere. And what this allows for is weakly coupled plasmas. Then we have bulk interactions. So the plasma's physical size, when it comes out of a plasma jet, for example, if we have this plasma jet over here, the plasma will be maybe around this tall. The plasma's physical size, that length I just showed you, it's abbreviated L. And the Debye length has to be much, much shorter than the plasma's physical size. So the Debye length is abbreviated lambda d, and it has to be much less than L, or the length of the plasma itself. And what that means is that the interactions in the bulk of the plasma would be more important than the interactions at the edges of the plasma. And I'll talk about this a bit more in a future slide, but that means that the plasma is quasi-neutral. Next, we have the collisionlessness condition, which basically states that the electron-plasma frequency must be much, much larger than the electron-neutral collision frequency. And that makes sense, because collisions in plasmas are rare, because plasmas, as I said earlier, are ionized gas that meet a few more conditions, and at that temperature, those collisions are pretty rare as compared to in a gas, because the particles are moving very quickly. And that means that the electrostatic interactions dominate the processes of ordinary gas kinetics. So the last thing I'm going to talk about with regards to the definition of plasma is the Saha equation. But to get to the Saha equation, let's first talk about ionized gases. So an ionized gas has three types of particles. It has neutrals, which are atoms, molecules, and radicals that have no charge. It has electrons, which are negatively charged particles, and it has protons, which are positively charged particles. So the degree of ionization of plasma is said to be the proportion of the number of charged particles to the number of particles in total. And so that would be basically the number of particles that are charged over the total number of particles, including the neutrals, the electrons, and the protons. And for any gas in thermal equilibrium, the expected amount of ionization would be given by the Saha equation. So the Saha equation describes the equilibrium situation between ionization and ion-electron recombinant rates. And this formula over here is the simplest form of the Saha equation I could find. And there are a bunch of constants that go into that, and they're all on the right-hand side of the screen. Okay, so now there are two major types of plasma. There's thermal plasmas and there's non-thermal plasmas. Thermal plasmas are said to be at thermal equilibrium, which means that they have electrons and heavy particles at the same temperatures. Non-thermal plasmas are said to not be at equilibrium, which means they have ions and neutrals at lower temperatures, which is closer to the gas temperature, and electrons at higher temperatures. DBE plasma, or dielectric barrier discharge plasma, is a non-thermal, non-equilibrium plasma that's used in medical applications due to its low temperatures. So there are multiple applications of plasma in medicine. It's used to sterilize medical and dental devices, as well as sterilize fruits and vegetables for them to be sent to be eaten. It helps in the dental field with the treatments of teeth, gums, and nerves. It helps on the skin with wound healing and sterilization. And it helps detoxify wastewater so that we can, and exhaust gases so that we can send that back to be reused. So I talked a bit about how plasma would be used in the medical field in wound healing and sterilization. But I guess the question that comes up then is what really happens behind the wounds or what really happens with the plasma behind the wound that allows the wound to heal quickly, or that allows the wound to be sterilized. And there are a couple of theories about that. First, Friedman and Chen, in their research, they found that the plasma plume emits a reactive particle called reactive atomic oxygen, And when this particle reacts with the water in the blood, that produces hydrogen peroxide, or H2O2. Hydrogen peroxide will interact with the tissues in the body, which increases their oxygen tension, and that triggers the formation of fibroblasts and platelet-derived growth factors, which allows for inflammation and angiogenesis, and thus wound healing and sterilization. The next thought is that radicals in the plasma allow for the creation of cell mediators like nitrogen monoxide, and those support the tissue's healing mechanics. Larusi et al. In their research found that UV radiation and the reactive species in general found in the plasma are very important in bacterial inactivation. And then there's a company called Plasma Surgical Inc., which uses these reactive and oxygen nitrogen species that are present in the plasma to locally reinforce natural physiological processes. So while working in surgery, these doctors are able to use plasma torches to heal internal wounds in the body. So dielectric barrier discharge plasma is created when two electrodes are separated by dielectric material. So we usually create our electrodes with copper tape, and our dielectric material is just this small dielectric tape. It's really not that thick, the size of regular tape. And so we have these two electrodes that are separated by dielectric material, and we pass a helium or argon gas with nitrogen and oxygen additions as the working gas for the plasma. But in the case of a surface dielectric barrier discharge, as we'll show you in this demonstration at the end of my presentation today, it can also be created at this level with pure air. So we'll show that to you at the end of the presentation. But basically we have one covered electrode, and then that is covered by dielectric material, and then we put another electrode on top of that at a small distance from the first electrode, not directly on top of the first electrode. And between the two electrodes, a plasma discharge forms. And it looks something like this. I don't know if you can see it, but there are very tiny gaps between the plasmas, like right there and right there. Those allow for the formation of what's called streamers, and that's because this plasma is created in the plain air. It allows, like, the interactions with the air allow for the plasma to break down at the edges, causing the streamer-like formation. So one more thing that DVD plasma does is it helps in aerodynamics. So plasma in the form I just showed you, plasma that looks like that, isn't actually used in the medical field. It's taken and then it's formulated into a different form that's less harmful, that's, I guess, less, the temperatures of plasma are very high, so I guess less hot for one. So it's taken into a different form and then it's used in the medical field. But this plasma, as it is, can be used in aerodynamics for flow separation over an airfoil. And this was a project done in the Princeton Plasma Physics Laboratory by Professor Zaidi and Professor Miles. So what we see here is that as we change the plasma's conditions, the airfoil, the flow separation will change from the airfoil. So over here, if you can see the video, as we increase the power, the flow is separating a bit, and then it comes back to normal. And then basically as we change the plasma's angle and the plasma's input conditions, we find different flow separations from the airfoil. Okay, now let's talk a bit about DVD plasma jet design. So DVD plasma jets, the traditional one used by most researchers is something along the lines of this. It's connected to a Lego for today, but you can pass this around. So this is the traditional DVD plasma jet, which is basically, it's been extensively tested by various researchers. And it relies on a small tube for gas ionization, and it has very low gas flow rates. And I'll come back to these low gas flow rates in a bit, towards the end of my presentation. And the plasma plume length is just a few centimeters long. Like I showed you, it's about that long, coming out from the end of the plasma jet. And the special thing about the torch that you guys are holding in your hands right now is that there's a syringe at the top. If you can see that, it's a syringe that can be pushed in and then pulled out, and we could use that. We've theorized that we could use that for medication. So while we're using the plasma on the wound, we can also, at the same time, pass the medication through the syringe in order to administer that to the patient. Here are some plasma jets, other plasma jet designs of the same kind that have been used by many researchers. So there are these ones and these two. This has been done by many researchers in the world. So it's not like our lab was the one who used this, but we've just gone off of other people's designs and tried to see if we could improve those. There are, however, a couple of limitations with this design. The first is that while we're running the plasma, we don't have any control over the plasma's parameters, and these parameters are the things that are the most important because these parameters allow for the creation of the reactive species that are used in the medical field. That are used in the medical field in wound healing and sterilization. And these parameters are kind of like what's important. So there's the reactive species presence, as well as the rotational, vibrational, electronic, and translational temperatures of the plasma. And while running this plasma, unless you change the operating conditions, you have no control over these plasma parameters. And that's a problem in the medical field because we obviously want to optimize this as much as possible. And so to overcome this, we came up with two designs, the variable electrode plasma torch and the multi-electrode plasma torch. Okay, so here's the variable electrode plasma torch. This design is by Dr. Zaghi. So he proposed that moving the outer electrode along the torch would allow for the plasma to change without a change in its operating condition. And it did work, but there is one small problem with that, which is while you're running this plasma, in order to change the plasma's parameters without changing the input conditions, we actually have to go in and we have to move that electrode. And that would be actively moving the electrode, but there is a way we can passively change it so that the parameters will still change, but we don't have to actively go in and move the electrode. And that is the multi-electrode plasma torch. It's very similar to the variable electrode, but now we have multiple outer electrodes. So we have one here, and one here. And we can decide to choose whichever one we want, and that provides a passive way to manipulate the plasma's characteristics. So now let's talk a bit about the power diagram for basically any plasma torch we use. So we have basically two 1000 to 1 high voltage probes. One that was used before the plasma and one that was used after the plasma. And we decided to use a 1000 to 1 ratio because the input AC voltage is several kilovolts, and our oscilloscope cannot handle that much voltage. So we use the high voltage probes in that sense. And we have two oscilloscopes as well. The first one is to measure the input condition, and the second one is to understand the phase shift between the first oscilloscope and between the first oscilloscope and after the plasma. And then we have a 100 kilo ohm ballast resistor that was used to limit the current in the plasma. And in the configuration that we have right now, after the plasma was measured, we use this to obtain the the phase shift. And power was estimated using formula P equals VI sine phi, with our typical plasma power being now on to characterization of the plasma, because there are many ways to test how well plasma works, and it's important to look at those to see if our plasma actually has the best operating conditions possible. So our first test was plasma luminosity measurements. Basically, we take pictures of the plasma torches and we look at how intense how intense each basically pixel in that image is in order to see if the plasma is like radicals, if the plasma is strong enough. And so what we found is that plasma plume intensities are measured as a function of applied voltage. And what that basically means is that this black line at the top is around 6 kilovolts. It comes from this plasma over here. And this orange line comes from this plasma over here with an input voltage of 4 kilovolts. So we developed a MATLAB program to measure these pixel-to-pixel intensities. And we found that the plasma intensity does not remain uniform as the voltage is increased. So lower intensities tend to be around the plasma plume that has a lower voltage. And the plasma plume is more turbulent as the applied voltage increases. As we can see, we can kind of see that in this image over here. Yeah, we can kind of see that in this image over here. The plasma in that image is changing a bit, and that's why some parts of it are so bright and others are so. Next, we have the plasma temperature measurements. Basically, we took a K-type thermocouple pictured here, and we passed that through different heights from the plasma jet exit in order to see the gas temperatures for the plasma. And what we found is that closer to the plasma jet exit, the gas temperature is higher, and increasing the voltage will increase the temperature. So, for example, take these two. Take these two graphs over here. The blue lines in both graphs are from plasma made with an input of helium of 20 cubic feet per hour. And over here, the highest temperature at a distance of 0 from the plasma jet exit is 50 degrees Celsius, whereas over here, the highest temperature would be 40 degrees Celsius. So we already see that decrease. And then when we look at the different flow rates, the different helium flow rates, we see a steady decrease in plasma gas temperatures as the flow rate increases. Again, on plasma gas temperatures, we did another test. This time using 3 different outer electrodes. At different points, we connected the plasma to different outer electrodes. So electrode 1 would be this one over here, electrode 2 would be that, electrode 3 would be that. And what we found is that electrode 1, which is the closest to the plasma, has which is closest to the torch, has lower gas temperatures, lower gas temperatures than electrode 2, which also has lower gas temperatures than electrode 3. And that makes sense because electrode 3 is closest to the plasma jet exit, which means that the plasma will probably come out with more force from electrode 3 than it would from electrode 1. And then now I'm going to talk about another technique that could be used to monitor plasma.
Krishnaveni, did you want to pause for a minute to see if there's any questions?
Yes, does anyone have any questions?
Do you have any questions at this point?
Yes.
I was wondering, you say the plasma is safe for medical use. What is like the temperature of the stuff that's actually safe?
So, okay, that is a good question. So we haven't actually used plasma, let's say for medical use, in our own lab. So I wouldn't have the answer to that, but I'd love to find out more about it if you could.
Oh, okay.
It's around 35 degrees centigrade is max.
Really?
More than that, tissue will burn.
Because they use it in a different
70%.
form than what we use in our lab.
So that's why she's measuring the temperatures to see what is the best operating conditions which safe for the wound to expose.
'Cause it
Otherwise
won't burn.
your cells and your things will burn. So
Yeah.
there is a limitation of the power, input power, and there is a limitation of the temperature.
That's why you need so much
That's
control.
why she needs to measure everything. These are gas temperatures. These are the other temperatures are other which she will explain. So these are very important for.
Thank you.
Yeah, these are like points for future work, right?
Yes.
You mentioned a lot about the voltage of the power going into the test apparatus. how would the frequency of that signal affect it?
See if you have input.
What's that?
The frequency.
It's
The
an AC
frequency is
signal.
usually 20 to 40 kilohertz.
Okay.
That's the range. And naturally, when you change the input power or voltage, the frequency also varies with it. So for her experiment, I probably see that she always measured with oscilloscope what is the frequency when she changes the voltage, and then I think there is a graph which she has brought, voltage versus frequency, but usually the range is 20 to 40 kilohertz. And that is a pain as well because it affects the oscilloscope. It's a RF signal, so we have to shield everything. Otherwise, there is electronic noise which goes everywhere.
Okay. Any other questions? Yes, so the next thing that we used to characterize our plasma was emission spectroscopy, and the idea here is that plasma has a bunch of radicals in it, and the best way to measure the levels of these radicals is to see the emission spectrum, because the emission spectrum will give at what basically wavelength there are like peaks in at whatever wavelengths there are peaks in the emission spectrum, there will tend to be radicals that are associated with those wavelengths, and by measuring those we can understand how well our plasma is doing in creating reactive species. So this is a typical helium plasma emission spectrum, and we've captured this using an ocean optics UV-IR spectrometer, and that was calibrated using a standard helium-argon emission lamp. We took this with an integration time of 1 second, and we've identified several lines like the OH or hydroxyl radicals, the nitrogen second positive system, the nitrogen 2 molecular line, and the oxygen 1 line, as well as various excited helium lines. And what we did, we took these lines that we found and we varied the electron position between the outer electrode 1 and outer electrode 2. Outer electrode 1 is at the bottom, outer electrode 2 is at the top. And what we found is that by changing the electrode, there is a difference in the intensities of each peak. So the intensities in outer electrode 1, which is closer to the plasma jet exit, are much higher, except in the case of this dark blue line over here, the hydroxyl radicals, than the intensities in the higher up electrode, which is outer electrode 2. And to go one step further from our work on emission spectroscopy, we use a software called SpecAir to again analyze various parts, a specific peak that we took from our emission spectrum. And what SpecAir does is it allows us to define our own trapezoidal slit functions and manipulate these spectra in order to find the one of best fit. And that allows us to choose different translational, electronic, rotational, and vibrational temperatures based on the transition lines. And so what we have here is this blue line right here that starts here and ends there is the emission intensity of the plasma. It's what we got when we captured the plasma's intensity from the ocean optics UV-IR spectrometer. And then we fit 5 graphs to that. We fit 5 graphs at various rotational and vibrational temperatures, keeping the electronic temperature the same. And we found that this gray line right here, which corresponds to TR equals TV, or the rotational temperature equals to the vibrational temperature, equals to 500 Kelvin, is the best fit to our graph. And this was taken at the upper electrode at an input power of an input voltage of 5 kilovolts, a distance of 10 millimeters from the plasma jet exit, and with a 25 cubic feet per hour input flow rate. So overall with SpecAir, what we found is that closer to the plasma jet, vibrational and rotational temperatures will increase, and the lower electrode will have generally higher temperatures than the upper electrode. And closer to the plasma jet exit, when we put any of our instruments there, the plasma tends to arc, which causes unstable measurements. And that table over here just shows kind of like a summary of what I've talked about. Okay. I think the last way that we characterized our multi-electrode torch was using blood droplets. So we took a droplet of blood and we put it under our plasma to see how that would work. And then we took a look at that using a microscope, and I'll show you the microscope video in a minute. But basically, what the science behind this is that when there's a cut in the epithelium, or like a cut in the top layer of the skin, a clotting factor called prothrombin activator, as well as calcium ions, would be shuttled to the site of that cut. And the prothrombin activator will convert prothrombin to thrombin, which would be used to cleave fibrinogen to form fibrin. And the platelets will release fibrin, and that starts to close the cut in the epithelium. And the fibrin would be an insoluble protein that forms a fibrous mesh, which disrupts the flow of blood. And the fibrin would trap the red blood cells and seal the wound. And so, when we looked at this under a microscope, this is what we found. This is with plasma. So the fibrin networks are slowly forming, and over time, this is like a 1-minute video. Over time, you'll see more and more fibrin, and that will end up closing the wound. So this happens in 1 to 2 minutes, whereas without plasma, it would take around 10 minutes for fibrin to start to form. I'm just gonna let this video complete.
How did you take this video? Is this like synthetic skin?
No, it's actually a blood drop. So we took a blood drop and we put it under a microscope, and our microscope has some software that kind of records it to our computer. So we basically recorded it under the microscope.
And it's my blood drop. I put the needle and got it.
Blood, sweat, and tears.
How did you expose it to plasma? We put the plasma jet over the blood drop for different lengths in time. This was after 1 minute of plasma. But in the next slide, I'll show you different pictures after a bunch of different plasma exposures. And yeah, that's pretty much it. And then we put it under the microscope. And then the
So there's an exposure time of 1 minute, take the plasma torch away, and then see what
Yes.
happens? Gotcha.
That's true.
So this is what happens. As I said, I would talk about different plasma exposure times. So this is without plasma. This is with 1 minute of plasma exposure. This is with 2 minutes of plasma exposure, and that's with 3 minutes of plasma exposure. So you can definitely see that that difference in the fiber networks at different plasma exposures.
Yeah, I must add here that we are mechanical engineers and applied physicists. So we talk about these things, we have reservations. So I am speaking with Dr. Farwan Kazmi and Dr. Hassan Kazmi in a hospital, and they are looking at it, that is it the fibrils or they are dryness, because there is a heating effect as well.
Right.
And I told them that is there any way we can differentiate between, but they say that it looks like the clotting of the blood drop, because that will stop the bleeding, but we still have to investigate further. And we are looking for deep biologists, who can look at it, because mechanical engineer can do that much. After that, it's an understanding of the phenomena, how these things are coming up and what they are. But from the first guess and from the first discussion, we feel these are the fibrils which are really clotting the blood and stopping the bleeding. And it's accelerated as a result of exposure, plasma exposure. So if you have a plasma jet in your hand working on some battery, and you are in a battlefield or somewhere and you have a skin bleeding.
Well, I cut myself like every weekend, working, so,
Yeah, so you can,
Just
you
shoot
can,
it my way.
You can do it in the field, so that at least it will help to stop the bleeding, and that's the aim.
That's the purpose.
That's the
End
purpose
game,
of
yeah,
this
that's
whole
awesome.
thing. Yes.
So that's the number one purpose.
That's the number one.
That's last
This
weekend.
week's assignment.
Okay.
blood gods have to be happy, or I can't get it done.
Okay, so just a quick summary of the blood, whenever we did the blood droplets. So those images that I just showed you are basically like the surface of the red blood cells in the fibrin network. And these images, after the talks with Dr. Furwa and Dr. Hassan, we found that they display healthy coagulation. And with and without plasma exposure, they look similar at the end, but they look very similar, and the plasma doesn't harm the red blood cells. As well as without plasma, it takes a significantly longer time, like I said. With plasma, it takes about 1 to 2 minutes, whereas without plasma, it would take 10 minutes to even start the process. And the increase in coagulation rates might have also been due to the effect of the calcium in the blood. Because ionized calcium is needed in various steps of coagulation, and the plasma might be ionizing this calcium, making it readily available to use in coagulation. And further testing will involve the use of plasma on larger wounds.
The good point here is that when you inspect is without plasma, and then you look at with plasma, there is no difference other than these black lines. So it means that the plasma has no other immediate effect or other effect other than this. It just accelerates the process. And apparently, both surfaces remain same. And there is no any other feature we see when we expose it with plasma, except the accelerated rate of these fibrils they are moving. So that was the point which was raised by Dr. Farwa, that if plasma is damaging the cells, we should see it.
Right.
It's not damaging, it's just making it rapid, which is an encouraging sign. But we still need to look at it more. So, go ahead.
Okay, so we've understood our multi-molecular plasma torch, but there is one major problem with it, and that's that the plasma that comes out of this torch, right, it's about this long, right? It's 2 millimeters to 5 millimeters in diameter, although this isn't the multi-molecular torch, but it works the same way. It's 2 millimeters to 5 millimeters in diameter, and it's a few centimeters long. And if we're trying to scan, I don't know, a wound surface, like if someone has a really big cut, or if we're trying to scan a hospital floor in order to sterilize the hospital floor, that's very hard to do with this kind of plasma, with a very small plasma length. And so what we came up with is the DVD plasma sheet generator, which could be used in wound surface sterilization, or in sterilizing hospital floors, or in deactivating aerosolized bacteria, all of which I will talk about in coming slides. So here's the design for our DVD plasma sheet generator, and this is it going, in action in our lab. I'm passing it around this plasma sheet generator. So basically in this picture, we have 10 kilovolt, a 10 kilovolt 40 kilohertz AC voltage passed through a gas, a helium gas medium, and we have a sheet that's 50 millimeters wide in width, and it's about 2 millimeters thick, and it's pretty long. So that's much better than what we had originally in the multi-operate plasma torch. And it's much easier to scan wound surfaces or floors, for that matter. Before we go to any applications, I'm going to quickly characterize the plasma sheet in the same way I did it for the multi-operate plasma torch. I'm going to talk a bit about the temperatures, and then I'm going to talk about emission spectroscopy. So we took a K-type thermocouple in a 2D traversing system that looks like that. And we took the K-type thermocouple and we, at 1.5 millimeter intervals, we passed it through the plasma sheet. So we have one line here, then it goes down, another line there, it goes down, another line there, it goes down, and the final line there. And what we found was that in the blue line, closest to the plasma sheet exit, the temperatures were higher. And so we can find decreases every time we go further away from the plasma sheet exit. Along with that, it seems that closer to the center of the plasma sheet, there tend to be higher plasma temperatures than in the other parts of the plasma. Oh, and this is, it's very, like, I guess it kind of goes with the bulk interactions condition at a higher level, in that closer to the center of the plasma torch, we have better radical concentrations and better, like higher temperatures than at the other parts of the plasma. Next, we conducted emission spectroscopy again. So we used an ocean optics UVR spectrometer with a 1 second integration time. And what we found was that the plasma wasn't uniform across the sheet. The intensities were weaker at the middle for radical concentrations. So we took two wavelengths. We took 315.46 nanometers and 337.13 nanometers, and we analyzed the intensities at the middle of the sheet, the left of the sheet, and the right of the sheet. And we found that at the middle of the sheet, the intensity was much lower than at the left or the right. And then when we used spec air on this plasma sheet, we found that the electronic and vibrational temperatures were pretty similar, and the rotational and translational temperatures were pretty similar. The rotational and translational temperatures tended to stay pretty low and around the same value, whereas we saw drastic decreases in the electronic and vibrational temperatures as we got further away from the plasma torch exit. Any questions so far? Yes.
What is electronic, vibrational, rotational, translational?
So those are 4 temperatures that we get from our spec air analysis. They're temperatures that are used to make the Boltzmann curve. It's basically another way of analyzing these temperatures. So it's electronic, for example, would be the temperature at the electron. So when I started originally, I told you that there were 2 temperatures of non-thermal, non-equilibrium plasmas, one low for ions and neutrals, and one for electrons. So this higher temperature would be the electron temperature.
And these types of temperatures are specifically for plasma?
Yeah.
Okay.
Plasma will be defined by those vibrational temperatures, because inside ions and neutrons and ions, and all of them are vibrating as well. They're oscillating, vibrating, the translation movement, all of this gives them some sort of a temperature. So we say associated with the kinetic energies, and then you get the temperature. So why she is doing it? Because we need to exactly know that at one operating condition, what is the input voltage, what is the current, what is the power, and what is the gas flow rate, and what are the temperatures outside at various distances, so we can expose it at that particular distance to the wound. Also, we must know that exactly at that height, what is the concentration of various radicals and what are their temperatures. Then we can see the impact and we can optimize them. Otherwise, it's a blind thing and we do nothing.
Now I'm going to talk about aerosolizing bacteria and how we were able to create experimental data to investigate the plasma sheet's effects on aerosolized bacteria. So, just a quick thing, this is a picture of our experimental setup. We have a plasma sheet here and a plasma sheet there, as shown in that picture, with the plasma sheets inside the tunnel. We put an agar plate here, and we basically use a machine to create droplets. And those droplets are passed through the plasma, and then we see how much bacteria will grow with and without plasma. So what we found, or first, I guess, a quick run through of what we did. We used an ultrasonic droplet generator to produce droplets that were around 10 microns in diameter. And the mist with these droplets was added from the top of the test section, which basically was added in from over here. And once we added those in, we passed it through the plasma sheets, and then it was collected on an agar plate that was then incubated for 24 hours to grow bacterial colonies. And these droplets entered the rig from the top, and a fan at the bottom directed them towards the agar.
So the aerosols has the bacteria in it. So we grow bacteria in the liquid, then make the droplets then see them on the agar plate. There are tons of colonies. When this aerosols are mixed with some air or some fan, right, to push it down, pass through the helium sheets, these plasma sheets, and then we collect it, then nothing appears. 4 colonies, 5
Yeah, so
colonies.
when we
So which means that the plasma is actually eliminating the bacteria of the
So it
aerosols.
won't be infected. It won't-
Yeah, so this is basically
This is
for
for
the-
installation.
another application that can be have aerosols. If they have bacteria, can we pass it like in aeroplane if the you know in the tunnel, if the air is coming, if we can put it there some sort of plasma sheets, then it will kill the bacteria. Because the aerosols are micron size and they may have bacteria, and that's another application. But because we were doing sheet, so we started looking that can we really. This was the IEEE work presented by another student, Bhavya, she's in Columbia now, and that was presented by her. So that shows that how effective these plasma sheets are, and they can kill micron size bacteria without any problem. Yeah, that was a good result. We're still working on it and see how we can improve it. Yes.
So another application of plasma is in floor sterilization. So in hospitals, clean environments are very important because, like in ORs, you need a clean environment in order to make sure the patient doesn't get any other infection as a result of a non-sterile environment. And in order to do that, we can use a plasma scanning robot that basically travels along the floor in order to sterilize the floor. So this robot is able to carry 3 plasma sheet generators, and it carries the power supplies that are used to ignite the plasma, the instrumentation for the plasma, and its control for motion. And it's currently being tested for its effectiveness in eliminating surface bacteria. But while we have it, let's just watch a video. So that's our robot. It's basically walking, driving, I guess, along the floor, and then it'll stop and it'll make a turn, and then it'll keep walking.
Oh my God, that's so cool. It's a plasma robot.
Yes, it's a plasma room. What a name. Yes.
That's cool.
You were saying that the plasma doesn't affect human blood cells. How does that work when it will kill bacteria?
Yeah.
So the plasma, so the plasma has sterilizing effects. It's able to kill the bacteria because it has radicals that are able to sterilize the bacteria. So the radicals itself are able to be used in sterilization, but these radicals also help in the wound healing process. So with the blood cells, these radicals help in, I guess, forming the fibrin or ionizing the calcium in order to heal the wounds. But in sterilization, it is used to these radicals are used to sterilize the bacteria.
Actually, it's a very intelligent question because there are research papers and they are still looking at that what happens when the plasma hit the bacteria and the wall of that bacteria. So there are ozone, O3 is generated as a byproduct of that, and that ozone is killing some killing one. It is very hard to differentiate how much and which radical has really killed it. It is I don't find any paper to quantify. It's a very intelligent question, but yes, this is a question which need to be answered, whether it is a ozone or which kind of radical is actually hit the bacteria, the outer shell, and kills it and grows it. But yeah, that's where the research is at the moment.
Okay, so the plasma sheet generator has one problem. It's a very good instrument, but it has one problem, and that problem is that when we input gas from this end and the barrel is about that big, a lot of gas goes into creating that plasma, and as a result, this has very high gas flow rates. So we created the, I designed the multifaceted plasma jet, plasma torch, which I'm gonna pass around again. So, the idea behind this is that it has 4 very small single plasma torches, or single multi-electrode plasma torches, that are able, that the user is able to choose between in order to, 1, target the wound properly, and 2, reduce the amount of gas that we use, because if we use a lot of gas, then we won't have that much left to continue testing our work, and that's become a problem for us, in that we recently ran out of our helium supply, and now we had to switch to argon. And so it's easier to use the multifaceted plasma torch. This one, it's currently being tested. We got it recently. The other day, I turned it on in the lab, and I was really happy at how it worked. This is a picture. We connected it to 2 of the electrodes, the 2 kind of like closest to each other on opposite sides. And that's kind of how it came out. So I'm really happy with the results.
So when the plasma jet hits some surface, right? So it sort of work in a, if we put a dish there, you will see a circle is, this black circle appears where all the bacteria is dead, and that grows. So the idea is if you have 3-4 of them, and probably the circle will intersect and will cover everything rather than huge helium flow rate. Helium is not available. I'm tired of searching helium now. So we are moving to argon, and it's little harder to, ionization potential is different, so it's harder to make that. So, but helium is the easiest to work with.
Thank you very much.
So the last way to test anything that we have with plasma is with bacterial growth. So in order to test the bacterial growth, we do something called a serial dilution. This isn't the exact serial dilution that we have, but it's a very, it's a good image, so I thought I'd put it on our slide. What we do, we take, we have this medium, a growth medium called Luria Britannia broth, and abbreviated LB broth, and we put about 1,000 microliters of LB broth in the first test tube, and we have 7 test tubes. So we put 1,000 microliters of LB broth in the first test tube, and then in test tubes 2 to 6, we put 900 microliters of LB broth, and then in test tube 7, we put 800 microliters of LB broth. And the reason we do that is because when we're doing the serial dilution, we take 100 microliters from each test tube over to the next, and when we're taking 100 microliters over, we want to have an equal amount of solution in each test tube. So we'll have 900 microliters across, and that's why we have those different numbers at the beginning and the end. So in the first test tube that currently has 1,000 microliters, we take 1 colony forming unit of E. coli bacteria that's pre-grown. We buy that off the internet. So the pre-grown bacteria goes in, and it's mixed properly into that first test tube. Then 100 microliters of that is taken and put into the second test tube, and that continues all the way until the 7th test tube, which now has 900 microliters by the end of it, and everything's mixed properly. Now we take all the contents of each test tube and we pour them into a Petri dish full of agar, and then we spread it around the Petri dish, and once we're done, we end up with something that looks like this. Basically, we have this Petri dish from tube number 1 it's not treated with plasma at all, but it's full of E. coli colonies. I know you can't probably see it right there, but every tiny small dot you can possibly see on the screen is an E. coli colony. And then once we did 3 more serial dilutions, we got to tube 4. Again, not treated with plasma. This is the Petri dish for that one. There's also a lot of colonies on that one. And then by tube 7, it's so diluted that we have, I think this plate has around 18 visible colonies, maybe a bit more. And that's not treated with plasma. Now when we treat it with plasma with argon, plasma that's made with argon, we have, this is the Petri dish from test tube 4, and this is the petri dish from test tube 7. This petri dish only has about 2 visible colonies, and it's much smaller and much less than what was in the petri dish from tube 4 without plasma. And then we have this petri dish from tube 4. This was treated with argon plasma with oxygen additions. So right now we have even less colonies than with just plain argon plasma. And this one from test tube 7 with argon and oxygen additions, we have no colonies here. So this is like perfectly sterilized bacteria at that point. And as we vary the oxygen and nitrogen additions in this plasma, we have different like changes in the amount of sterilization in this in these petri dishes. So we hope to like test that in the future, based as a function of like nitrogen and oxygen addition. So just to conclude, I guess this part of my presentation, basically what we've talked about so far is what really DVD plasma would be, and the suitability of this plasma for medical applications, and different kinds of plasma torches and their limitations, including the single DVD plasma jet, the variable electrode plasma torch, the multi-electrode plasma torch, the plasma sheet generator, and the multifaceted plasma torch. And then we've talked about aerosolized bacteria mitigation and the plasma. We call it the plasma hoover, but I guess plasma Roomba works too. And then we talked about the protocol on growing lab bacteria and the plasma's impact on the growth in the petri dishes. Okay, now I'm going to do a quick demonstration of the plasma. So if you remember, this is the input power circuit that I showed you towards the beginning of this presentation.
Actually, you should show the first one, where
You're right.
the jets are. Yeah.
Let me quickly go back.
The first one.
Here we go.
Yeah, this is.
it. Okay.
No. There should be more. Go up. Go up.
Oh, you mean this one?
Because that's what.
This one.
Yes, that's what you will
Okay.
show.
So we're going to show you a surface DVD plasma discharge. Okay. So this is a surface, just any plain white surface, it really doesn't matter. These 2 wires that come out of it really don't matter. That's just whatever surface we found. There's one copper electrode here, which is, there's one copper electrode here, which is, then on top of that we placed a dielectric tape over there, that big roll. Yes, that one. And then we placed another copper electrode outside that. This one's, like, I can touch it, it's exposed to the air. And then we connected this with the, we connected this to the outer electrode to the 1000 to 1 voltage probe, and we connected the inner electrode to, no, we're good, right? This didn't come out anywhere.
That's okay.
Okay. Okay. And then we connected the inner electrodes to, we connected the inner electrode to the 100 kilo ohm ballast resistor, and now Dr. Zaidi is gonna turn on, the power supply, and then I'll show you the plasma. Well, just give us 1 minute, we're, something came disconnected really quickly. Just pull that out.
All right. If nothing explodes. I'm not any.
We are all yours now.
All right, thank you.
We can all heal ourselves.
Okay, all right. Hold it here. You have to turn the lights off for a minute, for 1 second, 2 seconds, 3 seconds. Okay?
Ready, when you move.
Ready. Slide on it, maybe?
Down.
There we go. that should be good.
Fire.
Okay,
Hey,
you guys can
here
see
it
there's,
comes.
yeah, the plasma formed
Pretty. Wow.
the two.
What's this?
Hey, it's purple.
Yeah. Due to nitrogen breakup. So basically, there is a very interesting thing that Russians put these big dielectric discharges. Turn the lights off on the big on the wing of aeroplane, and control the boundary layer and separation of flow over the wing. What she has shown in the beginning, that it can actually control the separation, and you can increase the angle of attack of the aerofoil. They actually landed without using any other thing except controlling the dielectric barrier discharges. But the problem is, if it is raining or humidity, then it's done. Then you are down. So, but that was a demonstration that this is so powerful that you can actually control the flow and boundary layers over the aerofoils of a flying aeroplane. And they very successfully landed. There is a good article on it actually. Yeah, okay, thank you.
So just a couple of acknowledgements at the end of our presentation. The material I presented today has been borrowed from books on plasma physics by Yuri Razor, Francis Chen, and Alexander Friedman, along with research done by the Princeton Plasma Physics Laboratory and research done by Plasma Innovations LLC, along with some of my own research. And thank you to Dr. Zaidi for mentoring me as I did this research. And thank you to IntelliScience Research Institute and San Jose State University for providing me with the materials and resources to carry out the research I've done. And then here are my references, and thank you for listening.
Excellent.
Yeah.
Recording stopped.
This is very informative, but I think we have some people in remote. Maybe you have time a little bit to.
Yes, I do.
Yeah. Just have a check.
I stopped recording with you.
Lots of potential medical applications.
Yeah.
I want to see that. I work for the FDA.
So
Medical
she is
devices.
basically she is in 10th grade and was going 11th grade. She's going to 12th. But at 10th grade, she has been admitted to MIT. She's joining MIT this year.
Wow.
So even before finishing the school, she has been admitted. So.
We have some questions online that you can respond to. You want to listen?
There are no questions.
Yes?
There are no questions.
No question? Okay. All right.
Yeah, I
Thank
appreciate
you.
All
it.
right. Thank you. Thank you.
Thank you very much. That was very good.
Of what I'm seeing, you know, so like, I hope it
So I'm in 11th grade,
You have to
but
go.
I